We have with us three very interesting speakers today that I'd like to introduce. Starting with myself, I'm currently with the managing principal of Ctbuh, which is a very large firm in the United States, and I'm the managing principal of architecture and design. For me, that's a very interesting opportunity to take a long history of my career in high-rise buildings and see if I can't get my arms around a larger firm to apply it to exactly the same issues we're all focusing on here in Mumbai. Our next and final speaker is Dr. Volker Buttgereit, and he will speak on the, he has a new topic actually, it's the dynamics of the wind within the building frame.
All right, good afternoon. Well, sticking with the theme of sustainable buildings, I decided to take this opportunity to share some of our experience on large-scale building integrated turbine design, which is something that we first concerned ourselves with when we were assisting Atkins on the design of the World Trade Center building in Bahrain and Manama. And there's some, the object of the presentation really is neither to promote nor discourage implementation of this technology, rather than taking you through some of the generic ideas that from a wind yield optimization point of view you need to go through. So this slide really sets out the key aspects that you need to consider, and it really starts with getting clear in your mind and your client's mind how much wind energy you really want to pull out of a building integrated wind turbine arrangement, and from that really drop out all the other key questions that you need answers to. So you, in the first place, need to consider the local wind climate, which may or may not be appropriate for building integrated turbines. You need to consider very carefully the wind energy conversion technology, what type of wind turbine is available to you, at what scale, if this is something that you're interested in. You need to consider very carefully the building aerodynamics, which obviously interacts with flow around the turbine and ultimately decides on how efficient the device is going to be in situ of the building. And we saw a good example of a real-life project before where that was relevant. And you also need to decide what you are going to do with the energy that you extract from the wind. Are you going to feed it back into the grid? Are you going to store it in batteries? Are you going to use it in any other form? Because that really decides some of the key issues that need to be addressed in the integration process. You need to think about grid connections, that sort of thing. This slide here is actually, I'd say, one of the most important slides in my presentation, and I say that because not unusual for us to come across projects where there is a very serious mismatch in expectation about how much energy you can get from building integrated turbines and the scale of devices that designers are considering. So if you start off with the top left-hand corner, you have a relatively small-scale device, a turbine of the order, say, 3 to 5 meters in diameter. Now that scale device is going to give you no more than 11 kilowatts. That's what these machines are designed to deliver at rated wind speed, which is the wind speed at which they operate at maximum efficiency. You really, if you're considering extracting a reasonable amount, a meaningful amount of power from the wind, say 10% of building consumption, you're talking about devices which are rated in the order hundreds of kilowatts. So if you look at the other turbines there, if you're talking about hundreds of kilowatts, you are immediately talking about devices which are tens of meters in diameter. Typically, 30-meter diameter turbine gives you something like 300, 400 kilowatts. In Bahrain, they installed 3 30-meter diameter turbines, which ultimately gave them a rated power of about 1 megawatt, which amounted to something like 12% of the energy needs of that building. So if you have a design intent of extracting something of the order 10% of energy from the wind and supply it to your building or to the grid, you're talking about large-scale devices. And really many of the thoughts I outline here are relevant to that sort of a setup. And it really needs a positive decision from the client team and the design team right at the start of the project. This is the way you're going to head, because very serious engineering challenges that need to be addressed, and you need to let this design intent to some extent guide the design of the buildings. If you want, if the decision is to more or less have a feature which demonstrates green design intent, by all means take a small turbine, put it on the roof of the building, just make sure it doesn't disintegrate or blow off, cause vibrations or adverse effects, noisy, do that, but much of what recognize it's a feature. I'll talk briefly about wind turbine aerodynamics. The graph on the left shows on the y-axis turbine efficiency, on the x-axis wind speed, and the different curves are for different types of turbines. So they are vertical axis machines, they are horizontal axis machines. Vertical axis machines have the benefit that if they're placed in open air, they don't have to pivot and align themselves into the wind. They are generally not commercially successful in that they have a tendency to fatigue because blades travel through each other's wakes in the wake of the rotor. So while in the past there have been some commercial machines, most of them are now withdrawn from the market at large scale. And the only vertical axis machines really available at the moment are relatively small scale machines. But they all have different aerodynamic operating regimes, i.e. wind speeds at which they produce optimum power. Note that the maximum theoretical efficiency of a wind turbine in the wind is 60%. They're the laws of physics. Wind turbine, an unducted arrangement in free air, cannot extract more than 60% of the available energy based on the swept area of the rotor. I've put two equations down there. Turbine performance is characterized through the power coefficient Cp, and the power you extract from a turbine is proportional to the wind speed cube and directly proportional to the area. So if you want to double the amount of power that you pull out the wind, you can double the area of the turbine, and you get that for a given wind speed. It's important, in the context of building integrated turbines, the fact that the power is proportional to wind speed cube is interesting because you realize that wind speed increases with height. If you can put a turbine high up in the wind, you double the available wind speed, you multiply the available power by a factor of 8. So I guess that's one of the attractions in theory of putting large-scale turbines on buildings, because you can use a building to get the wind turbine high up in the air. I've mentioned the maximum theoretical efficiency that a turbine can see at 60%. That is true for wind turbines which are unducted and sit in open air. If you put a duct around it, and in some cases turbines operate in duct-like configurations on buildings, in theory you can get somewhat higher efficiency, but it's important to note really that if you are involved in a commercial project that requires this sort of technology, there are no commercially available ducted wind turbines out there, and all of the performance data that you have for off-the-shelf machines apply to an unducted configuration only. So some research needs to be done into what the aerodynamic performance of large-scale ducted turbines is. At the moment, it's somewhat of an unknown. Considering wind climate, if you were designing a wind farm, normally wind farm designers go to wind atlases. They're well established that tell you what the general wind speed distribution is, and from that you can immediately estimate your wind energy yield. If you're considering putting wind turbines on buildings, you need to do something a bit more sophisticated in your wind analysis, and that really starts with obtaining reliable long-term statistics for wherever your site is. And they're shown in form of the what we call the wind frequency data, and these plots show probability of wind speed bands against certain wind speed ranges, and clearly there's a big difference depending on where in the world you're planning to put the wind turbine out. So something that works in London doesn't necessarily work as attractively in Mumbai because the wind climate is different. These graphs show wind force. The other thing you obviously need to consider is directionality of wind. We had an example before where the wind turbines, when integrated into a building, were favorably aligned with the prevailing wind direction. So that's telling you that most of the time the wind turbines will actually be seeing wind through them. And again, that's quite key to the final number of your energy yield. The other thing you need to consider is that the wind climate data that you usually acquire is at something like 10 meters height. So in order for you to get some of the key input data to your wind energy yield assessment, you need to do some manipulation on it. And that starts with looking at the effect of height above ground. So wind speed increases with height. In terms of the wind probability distribution, it means your bar charts move more towards the higher wind speed end. So if you take your 10-meter data, which are the blue bars, taken to the height of the turbine, it turns it into red bars. So you can see you have much more frequent occurrence of higher wind speed bands. And some of the slides that follow tell you why that is significant. The other thing you need to consider is building aerodynamics, because there is speed up as the air moves around the building. You need to think about where you're going to put them. Ideally, you want to put them somewhere where the wind speed is high, so either flow over the top of the roof or around the corners, or if you have a twin tower arrangement, considering putting turbines in between the towers is interesting. You can have a ducted arrangement within a single tower, which generates funneling and all increases the wind speed. Remembering that power is proportional to wind speed cubed, so small changes to available wind speed make potentially a big difference to power that's available to you. So this graph, if you look at the windrows, shows more or less the speed up for a ducted type arrangement, not entirely dissimilar to the thought that in concept the arrangement that was shown before for Pearl River Delta. So the red curve shows the wind speed available to a turbine in open air. The two blue curves show the difference between a shaped duct, which has been streamlined to reduce the losses, and a straight duct. The interesting thing is that these ducts seem to be working over a relatively large wind angle range. Something like if the wind is something like 60 degrees off the axis of the rotor, it would appear that you can still get flow through there, but you're limited very much to that range. So this then tells you that you have another speed up factor to apply to your basic wind data. That then this graph shows also the shape of the power curve against the available wind distribution. And when you're optimizing a building integrated wind turbine arrangement, what is key is to try and get the best match between the shapes of those two curves. So you want the most frequently occurring winds to coincide roughly with the wind speed that your turbine is most efficient at. When you put in the duct, you need to consider that there are some wind angles, assuming that your wind turbine doesn't rotate with the wind, there'll be some wind angles for which the wind turbine doesn't see wind, so it's reduced from what is theoretically available. That's why the green curves have gone down relative to the red curves. You then have further duct losses to consider. But you can see in a duct the general shape of the available wind speed starts matching up to the shape of the turbine. These slides show the point of aligning the buildings correctly with the prevailing wind directions. If that is your prevailing wind direction, you're probably going to be all right because the wind most of the time goes straight through. If your building is not entirely aligned, you will have a problem of getting the air to go through there. This demonstrates the same principle. So really you want the red and the orange lines, which are the the speed up through the duct and the basic wind directionality to be aligned, and the difference between a positive and a good and a bad arrangement can be significant in terms of wind energy that you pull out. The point of this slide, this shows two different locations. We have considered a 35-meter diameter turbine placed some 200 meters in the air, and considered London and Mumbai. London is on average much windier than Mumbai, so for a given turbine it would produce a lot more wind energy yield. So the point of that really is that you need to consider that something that works in one location really doesn't work necessarily in another location, and therefore these are really bespoke design solutions. So if you consider different type turbines, the power characteristics change of the turbine, and you can consider different turbine arrangements to match it, produce the best match against the available wind speeds in situ. And you can see that change in turbine in this case in London produced quite a big change in the wind energy yield. Gave us some 30% more power, whereas in Mumbai it didn't make much difference. Which really leads me to the concluding remarks. Sorry, no need to refer to this. So, really, if you are embarking on a project like this, you need to start off with considering the wind climate very carefully. Are you in the right sort of location to consider such a project? If it's not very windy, on average, you're not talking about storm events, it's unlikely that you're going to get much energy out of it. In your design arrangement, you need to ensure that you have compatibility with wind climate and wind directionality and the building layout, i.e. building orientation. The third point is quite an important one as well. You need to accept that it's an integrated design process between understanding the wind regime that is available on the building and choosing the wind turbine technology and specifying the wind turbine technology. And that's quite a key thing, because most of the wind turbines that are commercially available are not off the shelf. They're bespoke design, and one of the biggest challenges that we had on the World Trade Center Bahrain project was very much obtaining the interest and commitment from the wind turbine designers and suppliers to get involved in the project, because as far as they're concerned, the off-the-shelf machine, the commercially available machines, are not compatible with the wind regimes that they see on these buildings. So they look at it very much as an R&D project. There is concern about the strength of the blades, there is concern about the turbulence that they're seeing. And these people you would normally expect to give warranties on these machines. So it's very, very challenging. And for that reason, really, if you are embarking on a project like this, you need to make sure that whoever you're going to procure the turbines from are really on board from day one and can interact with the building layout, because their performance is very sensitive to regime. And I will finish this up by having talked a lot about aerodynamics and aerodynamic optimization. It's something that, yes, I'd encourage you to think about, but don't obsess about it. There are many, many other very key issues to be thought about when you're embarking on large-scale building integrated turbines. There are noise issues, there are grid connection issues, there are mechanical vibration issues, there are a whole load of very serious engineering challenges, and aerodynamics is only one of them. A lot of the time we get involved in this, and people quite rightly worry about maximizing the energy capture that they can get from these turbines, but really, because it is relatively novel technology, remember that there are other things to worry about, and it may well be that you're well off incurring some drawbacks in aerodynamic efficiency at dealing with some of these other issues, and I will finish off with that.